Hello. Good morning. Thank you for coming, and sorry for the delay. It was a bit difficult to get here, but I hope the hangman was guiding you to the place. Okay. I would like to introduce a bit what's going to be the presentation. We are launching a new simulation product that is, we are very excited because it's something very new even for us. Okay, we have been working in collaboration with the NCAR for 2 years now, and this is, let's say, the first time this is presented to the industry from our side, because until now everything was in the academic side. Okay, this is the outline of the presentation. I will talk a bit why we as a company are here in this development, and then Alex, who's the man behind the code, will explain a bit the basis, and we'll introduce the validation. We perform a very ambitious validation in which Vestas had a very significant role, and then Mark will explain his experience with validation, and even in a broader picture of what LES is going to be in our expectations. Okay. At the end, we will have questions and answers, and at the end of the presentations, we will make the draw for the GoPro camera that many of you are in fact attending here just for the camera, I know. Okay. We are, in Vortex, we are obsessed with the time series. Why? By the way, this is our favorite program to analyze the measurement time series. It's called Value. It's from some friends from Brazil. It's a small company, and they developed this. Okay, why are we obsessed with time series? We think time series is the future. Time series has a lot of complexity, but right now they are not the standards. The standard in wind resource assessment are wind distributions, and wind distributions is a very, very rough simplification of what a time series. Because if you could have a time series instead of a distribution, you could discriminate, for example, by day and night. Prices of electricity are different in day and night. You could discriminate winter and summer. You could discriminate many things that once you have the distribution you cannot do. You could also cross-relate variables that once you have the distribution they are not there anymore, at least to be cross-related. This is a plot of turbulence intensity versus shear. This is very interesting for the manufacturers. We are active contributing to the power curve working group, and they are very interested in this kind of things. And if you don't have the time series, you don't know anything about ramps and any time-dependent phenomena. Okay? So I hope that after these 3 slides is very clear that the advantages of time measurements. What was not clear is that those were measurements. Those were not measurements. Those. Have you ever wished to have a time series of measurements at each position of the turbine? I think, well, of course, we are not there. We are improving and learning, but I think with LES we are in the way to get something very, very, very similar. This is part of the contest we sent to many people in a newsletter. We were asking the contestants to say which were the measurements and which were the model results. Many of what you are here, you were right, okay? But much others were wrong, okay? That's why you are here, because you were right. And only let's say people with experience can distinguish one thing from the other. I would say LES is we are at the beginning of LES, and we would like that this action from us will promote a LES community, and this is being growing and growing, because LES is very, very powerful, and it will be more and more when the computers get cheaper and faster. Okay, we will come back to this plot at the end of the presentation, also when we perform the draw. Why we are not using currently time series as in an operational way? Because you cannot measure a time series at each point of the wind farm, and if you could do this, it will be very limited in time. And where do the distributions mainly come from? At the beginning of the wind resource assessment times, the distribution came from the limitations of the computers, the limitations of the software. But right now, the distribution mainly come from the extrapolation of the wind field. The extrapolations of the wind field by CFD, WASP, any of these does not produce time series. Why? Because it's really computer consuming to do this. So we are working with distributions, which is a simplified thing, but it's useful. But we are now, the technology, the hardware has evolved, and we can use this. Okay? LES is, after our experience, is beginning to be one of the most measurement-like results that modeling can achieve. Right now, as Vortex, our main delivery is mesoscale time series. This is the thin line on the background. These are long-term, but they are hourly data, and you cannot go further in resolution in time if you don't go further in the resolution in space and you put some physics there. And this is our approach. The Vortex LES that we are presenting today is delivering physical 10-minute averages. What I mean for physical, there is no statistical approximation inside the 10 minutes period. It is real physics. It's a limited physics because LES is also limited, but it responds to the nature, to the scenario. Places with more turbulence in reality, less produces more turbulence. Periods of the day with more turbulence, LES produces more turbulence. Okay? We perform this. Alex will explain better. We perform very fine resolution calculations in the inner calculations. We go down to 4 Hertz, and then we collapse these 4 Hertz in 3-second samples. And afterwards, we average the 3-second samples in 10 minutes. Okay? But the 3-second samples have a lot of information. The standard deviation of the 3-second samples allows you to compute the turbulence intensity. And we also deliver the 3-second gusts. The 3-second gust is not parallel to the mean wind. It has its own behavior. It's like a teenager that goes away from home. Okay? Since this is a model, we can deliver 3D results. You can have results at each of the heights in this the first layer in the surface. This allows you to compute the wind shear. The manufacturers are very interested in this, and even the veer. Okay? And as I used to say, neither models nor measurements are the reality. The reality is much more complex. The measurements are limited. They are limited to certain heights, to certain locations, and model is much flexible in this sense, but it is not the reality either. It's just a guess of the reality. Okay, this will be my last slide right now, and this summarizes the characteristics of what we are delivering now as a Vortex LES. Is based, Alex will explain more, is not our technology. It's just a tailor-made version of a very reputed model developed in fact continuously developed in NCAR. Is a version of WRF that is our main our code that goes into the microscale WRF LES. We deliver 1 full year. We know that stationary effects are very important when analyzing a wind farm. So we deliver 1 full year. We could deliver the full year where you have problems in your wind turbines, or we could deliver a, let's say, representative year that has been chosen from the last 20 years to represent the long term. 10-minute averages, I said, 3-second standard deviation for speed and direction, and gaps. Other things are included here as usual, temperature, these kind of things. Okay. It's available everywhere. This is, let's say, and no measurements are needed. This is, let's say, a message for the CFD community. This is not. This is a complement for the CFD. CFD is producing fields, 2D and 3D results, and we are producing time series. So the time series is they can be an input for the CFD codes. These are time series of fake measurements. As somebody said, they could be used to when they evolve, they could be used to cheat people about measurements. Okay. We have performed a very ambitious validation campaign. With the results will be summarized later, and at the end of the characteristics, we are working. We are not a research institute. We are a company, and we claim to be very close to the problems of the users. So we decided that any Vortex product was going to be delivered in less than 1 week. So this full year of 10-minute averages, 3-second samples is delivered in less than 1 week. And now it's time for Alex.
Hi, can you hear me? Okay. The reason of this part of the presentation is to explain you the background of or the fundamentals of the WRF LES. And I know that probably here in this room there are people with different backgrounds or different approaches, and for this reason I will try to be more simple to reach to all people. Okay, in the atmosphere we have a lot of scales, from the large patterns that are the fronts or the extratropical cyclones that produce clouds today here in Hamburg, to thunderstorms that we have in the Mediterranean region, the wind that move the wind farms or the trees, and finally we have small eddies that move the leaves in the streets, that it's also a part of the atmosphere. Meteorologists define some characteristic lengths, spatial and temporal lengths, that describes these patterns. In each of these lengths, it's associated some physical processes, and meteorologists will define different scales that have different names. This is not most important for here, but in wind industry, the most important scales are the mesoscale, that goes from 10 kilometers to 1 kilometer, and the microscale, that goes from 1 kilometer to tens of meters. And also in temporal, wind industry is interested in all the physical processes that occur from 10 seconds, that it is the response of some of the data loggers and some of the controls of the blades, to the order of 20-30 years, that is the period of the lifetime of a wind farm. Then modelers, we use different tools for each type of scale. For climate, to study the climate, meteorologists use climate models to analyze the synoptic scale, that it is the large patterns in the atmosphere. We use global models, and for the mesoscale, we use mesoscale models, as the name says, that run using global models. This is useful because we can do a zoom in of physics and to have more information. For many years, since the 90s and 2000s, this was the main approach in the wind energy industry because the hardware resources were very limited. And firstly, people use models at 12 kilometers, then 9 kilometers, 3 kilometers, and now around 1 kilometer. On the other hand, since 2005, that time, people start using CFD models, trying to use also the information from the mesoscale model to understand better the microscale patterns, the local patterns and regimes of your wind farm. But there were a problem because mesoscale models and CFD models were not connected. This means that was not realistic because in the atmosphere we have all these scales interconnected, and they has feedback downscaling and upscaling, and this was not realistic. There are many types of CFD models, but mainly they try to simulate the energy cascade from the large eddies to the small eddies that dissipate the energy. Probably the most simple approach and cheaper is the RANS model, that means Reynolds averaged Navier-Stokes algorithms, that try to resolve the larger eddies, but all the more small eddies are parameterized. And this is very cheap. You have distributions, you cannot have time series of the wind and the turbulence in your site, but it's very extended. There are many programs that use this approach for computing the turbulence. Then you have LES, that is Large Eddy Simulation algorithms, that they can resolve more scales, but even all the scales that are smaller than the grid resolution should be parameterized. This has a more computational cost, but you have the good point that you have dynamic results. This means that you have time series and you can present some of the analysis that Pep showed before. And finally, you have DNS, that this type of algorithms can solve all the scales in the atmosphere or in a fluid, but they are very expensive in terms of computational cost, and has the good point that also produce time series. But here in this plot, you can see very fast, very quickly, the differences. This tried to be a plume, a small plume. When you use DNS algorithms, you have a lot of information of the turbulence of your plume. If you use LES, you can see the larger structures, but you cannot see the smaller eddies that you have in the DNS results. And finally, if you use a RANS algorithm, you only see the average of all these scales. And the applicability of each kind of algorithms varies depending of your application, of your interest. If you are interested in to understand the physics at the order of seconds, you need a DNS code. But if you only want to see the distribution of your region, you can use RANS. For this reason, we choose an LES algorithm to mix the mesoscale and the microscale. That this is what Vortex has been working during the last 2 years, because there are many problems to make the change between both scales. Anchor is working on this during many years. In fact, the WRF model, that it is a meteorological model, has a module for LES applications that in general it's only used for ideal cases. And in some small cases, people start working with real cases. When you try to apply LES in the real atmosphere, you have three challenges. The first one is the lateral boundary conditions. That this means that you are trying to run a microscale model using mesoscale information that has no turbulence. And this means that when you start producing turbulence in your domain, you destroy this turbulence by the boundary conditions that are affecting laminar information. Then you have a problem with the surface layer and the land surface model that try to produce all the patterns and all the physical processes that occur in the first meters of the atmosphere. And the problem of this is that all these approaches was made during the 90s and 80s when the mesoscale models start to run. But now for microscale applications we need more sophisticated approaches. And finally, we have a problem that it's called terra incognita, that this problem occurs when you try to increase the resolution of a mesoscale model, that there are moments that some of the approaches of the mesoscale model cannot be used, but the approach of LES is not useful yet, and this produces bad results. In Vortex, we have been working a lot in this part, in the first item, and because the other two are minor issues for create a realistic microscale time series, and Anchor is focusing a lot in these items. Here you can see the problem of terra incognita that I explained before. You have the mesoscale model, you have a large eddy simulation algorithm or another CFD code, but in this case LES, and there are regions that goes from 500 meters to 100 meters, where the PBL scheme that tries to simulate the first 1,000 meters of the atmosphere is not useful, but the LES code is not useful because you cannot see all the structures. Okay, focusing in our work in Vortex, here you have the mesoscale domain with a microscale nest. The microscale nest starts producing turbulence when you run the model, but the mesoscale model adds information, transmits information that it's laminar, and then when the laminar flow interacts with the turbulent flow, destroy all the turbulence. I like the example of water. Imagine that you have here a clean water, and you start and you start putting some color in the walls. After some time, you will lose all the clean water, and all the water in your tank will be in the other color. No, this is the setting, and for this reason, we have to search some way to modify the lateral conditions to conserve the turbulence inside your domain. And to do this, we create some clusters in the lateral boundaries of the domain, and each cluster we introduce a perturbation in the temperature that is compatible with the physical solution of the model. And this is good because when the laminar flow arrives in the boundaries, varies a little, and this produces turbulence. In the boundaries, this turbulence is artificial, although there are some physical sense, but as the model develops all the physics, this is adapted in the flow. Okay, say this, the approach of Vortex until now was to use reanalysis model to initialize mesoscale models until 3 kilometers, that it is a standard product in the wind energy industry. And now we change the approach, coupling a microscale model to the mesoscale model. With the microscale model at 100 meters, we get results every quarter second, that it is 4 Hz, like a poor sonic anemometer. And with all these 4 Hz information for a whole year, we compute some physics. To do this, we have a problem because in LES, as I said before, you solve all the eddies, all the physical processes that are larger than your resolution, but you cannot see all the smaller eddies than your grid. This is the subgrid eddies. I mean, each one of your grid points on your model, it's like a pixel, and you cannot see anything inside the pixel. Then we need, with this 4 Hz output, we only have the resolved eddies, and we need to introduce all the energy that it is associated to the subgrid eddies. To do this, we create a vortex flow composer that just take this information and include the energy at the smaller scales. And with this, we take 10-minute averages for wind speed, for wind with direction, for temperature, pressure, air density, etc., etc. We can compute the 3-second gust, also the standard deviation that is useful to compute the turbulent intensity, as you know. And we save all this information from 20 meters to 150 meters above the ground. And we have the temperature, pressure, Richardson number. The wind veer, for example, it's very important, and with a mesoscale model, you cannot evaluate it because you only have outputs every hour, but now with outputs every 10 minutes, you can see how the direction of your site changed, etc., etc. As Pet said, in Vortex, we want to show that LES is a good new tool, and we are validating a lot of sites. This is an old slide with 93 sites, but now we are working with 110 around sites. And one problem that we have when we validate the results, it is that in general all the sites has measurements of wind speed, but they don't have measurements of standard deviation, and then we cannot validate the turbulence intensity in all these sites. Here you have a map of all the sites that we are working to validate our product. And if you compute the metrics of some metrics of the results for all these sites, I will come back to this later. You get a mile in wind speed around 8.3% with respect to the average wind. A good metrics also for the A shape and the K shape of the wave, because in LES output, you can see that in general, in mesoscale model, you have a ball in your wave. This means that mesoscale model it's very bad producing the low wind speeds and high wind speeds. In LES, you can spread out your results, and you can see more extremes in your wave, and this improves the key. And finally, we get an R square for 10-minute outputs around 0.6, R square for hourly around 0.62, and finally for the daily results around 0.8. And one of the interests of LES results, it is the spectral density. This is a more physical result. But here, basically, you can see how the energy is produced in the large scales. Here you have all the motions that have a duration of 1 year. Here, 1 month, 1 day. This is the cycle, the daily cycles of the atmosphere. 3 hours, and finally 10 minutes. In green, you can see the real data that say that the energy cascade should follow this line. When you run a mesoscale model at 3 kilometers, you see that when you arrive around 1 hour, 3 hours, 1 hour, the model lost a lot of energy. This means that the mesoscale model cannot see the physical processes that occur at the smaller scales at 3 hours. And this is logic, trivial, because it is a mesoscale model and it's designed for that scales. But when we run LES, we improve the smaller scales, we get the energy that they should have. But we have a problem, a small problem between a half hour and 1 hour, and this gap in the energy is produced by the terra incognita that Anchor now is trying to solve. But this is better than the current approach using isoscale models. And finally, we also have been working with the turbulence intensity. When we work with turbulence intensity, we have many questions because as modelers, we have never validated the turbulence intensity, and we don't know how the sector or how the industry can understand these results. I mean, we are comparing two lines, but we don't find any metric in the sector. As in wind speed, we have or correlation or the waveful parameters. Here we don't have any type of common metrics, and probably you can help us to find it with your feedback of the results. But we define two metrics to validate our product. One is to compute the differences, the absolute differences in each beam for the turbulence intensity. But if we do this, it's not representative of the error because each beam of wind speed has a different frequency due to the waveful. Then we weight the final mite with the waveful probability at each beam. If we do this, we reach a mite of 82%, but it is not in percent error, it is an absolute error because turbulence, it is in percentage. And the other metric that we use that it's common within this CFD community is to validate the turbulence intensity in the 15 beam, that it is very representative of the European sites, but you can find different results at different places, and we get similar results using both methods. And that's all from me, explaining what is LES.
Thank you. Hello, my name is Mark Lagarde. I'm from Vestas, and I will show some applications and experiences we have had so far with applying Vortex LES scales down to 100 meters. We have been doing it for a while, and it was really natural. It felt totally natural to connect with Vortex, who found also an application in that. And now we hope to be promoters of this new technology together. And I will show a few slides why we think it's really useful. So how we are doing for the time being? What is the, I will call achievable accuracy of dynamical downscaling? Dynamical downscaling, this is the process of using the whole model chain from global to microscales to bring information downwards, to bring energy and information to the small scales, with making sure that as little of it as possible is lost in the transition. It is a very well known approach in numerical weather prediction. It means that you really use the global observations of the atmosphere in reproducing the state of the atmosphere at small scales. So it's, some people call it virtual, some people call it synthetic, but it's dynamic downscaling, and it's an important distinction here. So here I'm showing an example of the work we've done at Vestas to compare, it's a light comparison, but nevertheless, about 20 or 30 mat masts in Turkey that is known for quite complex terrain. Which one is the laser? Yes. And what I did is to compare the results, the comparison of the yearly mean average wind speed at these mat masts, depending on the resolution of the work I used. So it's easy to see that for high resolution, for low resolution model in complex terrain, we can expect the under prediction of the wind speed, just because the terrain complexity in the wind energy world will always add something, because you typically put a mat mast on top of a hill with the speed up. And this you don't capture in 3-kilometer model, therefore you have underestimation. It is also obvious from the bias. When you increase the resolution, you add effects of the terrain complexity, still using all the information from all the scales, but adding more terrain details that helps the model to have a better success at reproducing the features at these scales. So in this example, the green dots are from the 333 meter model. There's nothing special in it. It just high resolution of the typical work with boundary layer and everything. And bias has been reduced significantly. So that is basically a background of what also Vortex is doing. So downscaling, using all the information to bring weather to the microscales. Next example, also commonly used in wind energy, is to try to calculate the yearly energy production using a model in advance. So either having 1 or 2 met masts on the site or have no data at the site at all. So I took production data from about 30, 40, 50 wind farms, globally distributed, so in all climates, all terrain complexities. And I tried to calculate production at every turbine using a 333 meter WRF, and then sum the productions of all the turbines. So I was using WRF as a microscale model, basically. I used WRF to have information what the wind is at every location. So the blue dots show the distribution of error, of the precision of the prediction, if I didn't use any local mass data. So it's just model data, and we have some 16% error of mean absolute error, which is okay. It's not perfect, but it's useful, at least. When I add 1 net mast anywhere on the site to somehow normalize the WRF solution, the prediction was much improved. So that means that the remaining 8%, that is the microscale uncertainty of WRF at 333 meters. Again, it's a showcase for doing downscaling in the proper way. Additional example, just it is the last I promise, before I'm going to validation and comparison with Vortex LES results. So I'm sorry for the black edge. It looks nicer on my. So this is basically a site with a lot of turbines in a slightly complex terrain, but with very complex wind features. This is the wind speed at 80 meters. The wind is from northwest. It penetrates down the slope, so you can see the lines of the same altitude. So this is about 200 meters lower area than here at the Little Ridge. And what is particular here is that the pretty high wind speed managed to stop in a kilometer. So what happens is that basically the flow accelerates down the hill, and then it stops, it ramps up, like here. So this is a side view. This is a layer of moderate wind speed that is concentrated in a shallow layer, very close to the surface, maximum, and then it just lifts up. And this edge is propagating backwards in time, here we would show. And associated to this edge, so-called hydraulic jump, because it's similar to the hydraulic theory that is known for a while already. You can see it's, if you look from a bridge into the river and there are some stones and the water will jump over and make bubbles like this. So this is what happens. And here you can expect a lot of turbulence, a lot of very gusty wind, and also direction changes that go out of scale. That also causes, for example, wind turbines to shut down. So you will have emergency shutdowns because of the misalignment of the turbine rotor with the wind direction. And I have analyzed Vortex LES in terms of this later. So let's do this one. So and how good we need to be, how good we have to simulate wind. Even if we know the wind in the lower layer, so if we measure the gray area here, we still have to assume something if we are putting 136 meter rotors above here. So basically we don't know anything about the wind conditions here. We just assume that traditionally whatever shear we measured here, it will continue. Well, we need models to confirm or disconfirm this. So this is a model solution using just standard WRF of the yearly mean wind profile. And this is, we see how different it is from what we assumed by continuing with the same shear from below. And it's important because 2% of wind speed error, which is nothing, it's the precision of an anemometer, will cause 5% of production error. And that's really important when you go higher with taller rotors, called towers, that you have to match the additional production with the cost of the tower. So you have to know that this thing will be bigger than this thing in terms of money. And 5% is a lot. As a rule of thumb, So this is the plot of average error that we commit in Wyoming or something. So it's about 5%. 5% is a typical, maybe conservatively estimated error, but we commit by assuming the wind shear to continue from the surface layer upwards. And 1% of error on a 100 megawatt wind farm corresponds to 1 million euros. So it's costly. Okay, now, so how does the work LES do from Vortex? I have thrown some problems to it. So the guys in Vortex provided the LES time series. I compared it with the mass data that we have on a few examples. Not the worst, not the best, but challenging, and I will have some comments to each of these. So first of all, that's a map passed in Australia, simply considered in terms of the average wind shear and the diurnal evolution of the wind shear. You don't see the numbers, but it goes from 0 to 0.25. So we have low shear during the day, it's an UTC, and high shear during the night. And mean shear happens never. And nevertheless, I plot mean shear here with a coefficient of 1.173 in the measurements on the left, and in the model 0.169 on the right. So establishing this relationship, we have confidence that whatever model produces for above is, let's say, reliable, that we can use the model for that. And I also compared the windrows, pretty similar with some differences, but as it is a flat site, it's okay. So I actually used a flat site as a first example because flat sites are far from simple in terms of weather modeling. So we have significant errors in wind shear, in turbulence, and on flat site, depending on the climate and everything. So it's another, not so far from this one. Shear is again 0.24 versus 0.20. Windrows is okay, and the diurnal evolution of shear is okay again. Then we move to Scotland. It's a bit particular because of the mid-latitude climate. So we have storms coming. We don't have so clear seasonal dependency of wind regimes, etc. And I have some summarized statistics here. So first of all, you can see another nice example of the time series. Hard to say which is which. Matching pretty well. In terms of the scores, good, as Alex showed already. And I also included the monthly average wind speed measurements and the model. And also the differences between the two follow nicely the seasonal dependency. So yeah, it's another good example. But in the wind energy, as you know, we use turbulence information a lot. So far with normal models, let's say normal, we could measure scale models. We could get some idea about the production estimates. So we brought energy down, and we could predict what we will produce. But we couldn't predict what the loads will be. And that's what we need turbulence for. So that's why I also included a verification or validation, let's say on one case here, of the turbulence intensity rows. So this is the wind frequency rows. It's pretty similar, some differences, but normal. And turbulence intensity rows showing that whatever was measured, there is a peak in turbulence density from the west directions, and the model has picked it up properly. So the response of the point time series to the surrounding terrain is captured as well here. On the other side, we have some turbulence maxima that are not observed, but the wind frequency for these sectors is a bit smaller, so it's not so important, but it's nevertheless an interesting example to go in and study deeply where the models can be improved and how the future development, the direction they could take. And this is showing the, again, monthly average is turbulence intensity with a strange deviation in part of the autumn in 1 year only. So measurement 0.15, model 0.12. It is 0.03%. It's not so big, but it's significant, and I want to understand what happened here. So I just checked time series. It's always important when you have some perceived deficiency in a model to actually go in the data, have a look, and find a physical explanation of it, because usually you can find it. The worst thing you can do is to shout, oh, it's wrong. So the reason that I think, in this case, to underestimate turbulence in the model is that the wind speed was quite low for long periods of time. And if you just have a little bit of a wind speed overestimation, you will underestimate turbulence easily, especially with the low wind speeds. So I found that's a quasi reason for that. A very nice view of turbulence and performance of the model in reproducing it can be done in terms of the scatter plots. Plotting turbulence intensity versus wind speed. So each point is 1 10-minute data point, showing the cloud, of course, but also some outliers, which are, again, interesting to explain. So the shape is very similar. So the model has physics to reproduce whatever turbulence really happens at the site. It also compares well in terms of the mean turbulence density, but it has a little bit of the too big diurnal cycle. So in reality, there was not so much diurnal cycle at all in turbulence density. There is some in the model. So that's again something to have a look at. What is the convective generation turbulence doing in the model versus reality? And then there is another thing that load people like to do, to plot the mean bin turbulence intensity versus wind speed, and then add one standard deviation or 1.26 or something to have some load cases. Again, the shape of it, the similarity of the shape, again, indicates the performance of the model in this respect. And I would like to show one interesting thing. So on the Scottish side, you can see that for some reason, turbulence takes off at high wind speeds. But I don't think this is very strange, because imagine that at 15-meter wind speed, air travels 9 kilometers in 10 minutes. So the 10-minute standard deviation will contain motions from mesoscale, basically, that are not turbulence. So this is not turbulence. 27 and 30 meters per second. That can be 20-kilometer large structures. So I wouldn't call this turbulence. So we could stop at 15. Right. And then the site I showed before in the colorful plot. This is somewhere in America, showing really, really high turbulence at moderate wind speeds, just because of this hydraulic jam phenomena. And I throw this to Vortex to just test how that would perform. And I'm quite satisfied. Of course, it's not perfect, because this is a very complicated physics. You have to have a lot of things correct in the model and in your terrain to reproduce the hydraulic jams properly at the right time, at the right place. But what I was happy to see is that when I plotted standard deviation of wind direction, and that is something that a Vortex LES product can produce and is usually not observed on the matte masks. So what is the variability of the wind direction? And that is useful, as I mentioned earlier, to indicate problems, potential problems. So that when I compare the two plots for the Scottish and the American side, I can really see points with very high wobbling of the wind direction at moderate to high wind speeds, showing that the model captures some of these events. And that's building confidence in this kind of modeling. And also it's really exciting what the future development can do in this respect. I don't have time for this slide. So I just want to show one more, how you can perceive this as a not a good simulation. And of course, it is not so good. It has, so the less noisy line is the LES. The blue one is the measurements. So it is 1 week in July in India. It's a monsoon period, so it's really high wind speed. And the green one is the 1 hour data from our work 3 kilometer that indicates that some weather is happening. So it means that the time series, the LES time series, does not really capture the weather, but nevertheless it does capture, as the previous plots will show, if I show them, the average properties of the site. And that is something that you can already work with. But differences like that bring you a lot of new problems, new interesting work to do. And that's really, I would say, it's exciting to see where this will go. And we, as Vestas, we will continued to support it because we saw a big need to introduce more physics in microscale modeling, to not replace but to really complement CFD models, as they are called. Because this is also a CFD model. It's just not marketed as a CFD model. Good. So yes, here I will. This is where I stop with the question mark. Thank you.
Okay. Okay, I think now we will accept as many questions as you want, and then we will keep the price of the GoPro camera to the end, so then we can guarantee you stay here, okay?
Thank you for very nice presentations. I'm curious about how do you sell like a point time series, or do you sell like for a region and then an area or 3D field or 4D field or something?
Yeah, what we will deliver is a time series for a given point, and maybe for another point if it is very near. But we will not deliver the region because it is beyond our computational resources to store the whole time series for the whole points, and this is not yet here. We have to wait to a new generation of computers. This is not like the conference in the sessions in the conference, and there are not prepared questions. So if you don't make real questions, then there will be no questions and answers.
The question is for Mark. I'm Alberto Gil from Aqua Power. Thank you for a very nice presentation. It's very nice to see how the model, the LES, is matching the measurements with regards to turbulence intensity. But how far do you think we are, or the turbulence suppliers are, in order to accept LES to validate layouts without any measurements, or maybe large wind farms when there is only one meteorological mast and you have LES calibrated with the met mast? How far do you think we are to move into that?
I will say that when you don't have anything else, that would be very useful. And I don't want to comment on the rest. I think it's maybe to have the potential of the LES time series in like real applications. How ready is the industry to use it?
Okay. As I told at the beginning of the presentation, this is not the state of the art of what we experience with our users. The wind industry is using distributions instead of time series, and the software is right now not really prepared for time series. There is a trend I have seen in several software manufacturers to start accepting time series both for wind and for power. But this will come. This will come, I think, in the near future, and in the meanwhile we will try to improve what is the result. And this has already been applied now in a limited area, and I will tell you two examples, because we have already sold two of these time series. One was for a manufacturer, it's GE, in fact, Alstom. They had a problem with the turbine, and they had only measurements far away from the turbine, and there was not real a reliable way to extrapolate the turbulence from the measurements to the turbine. So we perform let's say a pre-sale of this, because we were very confident on this. So we sent them the time series at the place of the measurement, blind test. They compared against the measurements. They were satisfied, so they bought the time series at the place of the turbine with problems. Okay, this was one of application post-construction. The other one that we already saw was for a developer in Nicaragua. He had measurements at one point, but he was not confident of the measurements. He thought the measurements had not very good quality, so we sold them 1 year of measurements, in fact 2 years, at that point of of the MedMast. So with this, he was working for developing for Siemens, and then he was confident of that that data. And as I said also before, data, measurements, and model complement, and it is just a matter of acquiring confidence. Then it was you.
Yeah, thank you very much for the presentation. I think it's a big gap in this field. I would like to come back to the large eddy simulation modelization. I guess it's a question for Alex. What about the subgrid scale model? What do you use? Did you just choose one? Which one? Do sensitivity tests and so on?
Yeah, during these 2 years we have been working, testing a lot of the options that have worked, and in contact with Branko Kosovic, that it is the person in Anchor that developed the LES algorithm. And finally we use the turbulence kinetic energy 1.5 order approach for the subgrid, and we compute, we save the turbulent kinetic energy of the subgrid eddies, and then we introduce this energy to the final results to have the full turbulence approach. And for doing this, we use the stability and other physical parameters in a model that we have developed as a post-processing of the output, because we have the outputs at 4 Hz and then the subgrid, and we have to merge both to have the full turbulence.
Okay, thank you.
Very nice presentation. Thank you very much. Just a practical question. When this product will be available on the Vortex platform?
It is already.
It's already.
It is already. It is already, but with a special indication. People can because you must be aware that this is also a gap for us in computational resources. So this needs from 10 to 20 times the computational resources we were using now. So we are dosifying this, and users can click and launch a Vortex LES, but people who has a subscription, that let's say that they have a flat rate, not yet. Because if everybody gets crazy, then we collapse the system, and we will be in a very bad position. So let's talk, you have a subscription, so let's talk personally later. Any other question? If not, we go to the GoPro camera, okay? And this is, we made a contest, maybe some of you didn't participate, but the contest was, regarding 2 time series. One was LES and the other was the measurements, okay? Many of you did make the right answer, because, as Alex explained, there are some limitations in LES, and an expert eye can see. Okay, but this was because there were 2 lines. What if there is only 1 line? Are these measurements or model results? For example, it is clear for many people that this jump here cannot be produced by the model. This is the 2 abrupt jump. Okay, but this is not true. These are the model. These are the measurements. Okay, and the measurements have also another abrupt jump that was detected by many, because it was first. So this is the same time series in the contest. Okay, you could see if you there are two more clues to distinguish. This variability in the range of the terra incognita is not captured. So if you are used to see many time series, you could perceive this range in the light line. But there is another more interesting aspect, and this is the zeros. The model has no zeros. Why? because the measurements are wrong. This is very provocative, but the wind has no zeros, and you can see this when you measure with a sonic anemometer. The wind never stops. What stops is the anemometer. The anemometer, depending on the constant, distance constant, will stop and will show zeros. So, well, this was a clue. And many of you, we have invented a way to give the camera, and it's everybody who answered received an email with a number. It's the number of the participation. Okay. So I have here. This is just a download from the App Store. Okay. But this is a random number generator. Okay. And I will put the range of, because we made some tests at the beginning, I will put the range of the participants. And, okay. And now we shake this. This is for the camera because we will upload this, and we want to be very fair. Okay? Because not all the people that participated is here. There were a lot. So I will check this. And now we will see the number, and then Alice will check if he was right with the answer. Let me make this. Okay, no, but this can be. Give me a rest. 62. Okay, let's see if it was what he was. Only the people who justify the answer. They are worthy for the prize. Some people said stupid things. They are not. They don't deserve the prize. Okay, I don't have the email here. Let me see if I can see here. Sorry, I can't. Sorry for the mess now. I experienced also a mess yesterday, so I am 62. Okay, Peter Clegg is in the room. I think it's fair that Peter Clegg wants the GoPro. This is the GoPro. It's a pity he was not here, because then we can save the sending. Okay. So thank you very much, and you are very welcome to have lunch. It's our pleasure.